Hi students, so here you are going to learn about a new module. Okay, you are going to come to a new module, and here in this second module you need to study about 5 theorems. Okay, and those theorems are Thevenins Theorem, Norton's Theorem, Superposition Theorem, Reciprocity Theorem, and Maximum Power Transfer Theorem. These are the 5 theorems you need to study. Once you have covered these 5 theorems, then your second module will be complete, right? So what you need to understand from here is that you need to understand the concept of the theorem. You have to understand the meaning behind every theorem. Once if you are able to understand the theorem, then you will be able to apply that concept to any circuit. Alright, the important thing is no matter how difficult the circuit is, simply apply the procedure that I am going to tell you what it is today. Okay, so here all these theorems are very easy. It's very easy to understand and very easy to do the problems, as long as if you are able to understand the concept and also if you know the procedure of finding the corresponding values. All you need to do is understand the procedure. So here in this video, I'm going to cover the first 2 theorems. That is Thevenin's Theorem and Norton's Theorem. The reason is because these 2 theorems are siblings of each other. Or these 2 theorems are brothers and sisters. These 2 theorems. Once if you are able to understand one, then it is very easy to understand the other. That is why. So I will be covering these 2 theorems in this video. Okay, and last video you have learned about the source transformation, right? So what is source transformation? Source transformation means is that a voltage source with a series resistance is equivalent to a current source with a parallel resistor, right? Now let's see what is Thevenin's theorem. This is Thevenin's theorem. It states that any 2-terminal network can be replaced by an equivalent voltage source and an equivalent series impedance. That's all. Very easy. That is, a network, no matter how complicated it is, that network will be consisting of resistors, it will be consisting of capacitors or inductors or voltage sources or current sources or whatever. It will be a normal network, and according to Thevenin's theorem, that network, that 2-terminal network, that network supposed to have only 2 terminals. Okay, so that network can be replaced by a single voltage source and a single series impedance. Just look at the circuit. Here, if you look at the circuit, you can see that this is the 2-terminal network. This is the 2-terminal network. So inside this network there will be lot of other items like resistors or capacitors or inductors and voltage sources, current sources. All these elements are all interconnected. Okay, they can be interconnected however it is. It can be interconnected. So this is the network, and this network is connected to the load resistor. And this load resistor is what you call as RL. This load resistor, you all know what is load, right? Load is the output device or through which the output is connected. That is called as the load, right? So this is the load. Now look at this circuit. According to Thevenin's theorem, this network, this box over here can be replaced by a single voltage source and a series impedance. That's all. So this is a voltage source with a series impedance. The rest is the same. You see that same resistor is over here. RL, the load resistor is over here, but the only difference is that it is now this entire complicated network is now replaced by a single voltage, and that voltage we are naming it as VTH, and a series impedance that you name it as ZTH. This is what you call as the Thevenin's voltage. VTH is called as the Thevenin's voltage. Thevenin's voltage, and ZTH is called as the Thevenin's impedance. We write the capital letter V followed by a suffix TH. Here capital letter Z followed by suffix TH. Okay. So now what is VTH? What is the meaning of VTH, or how do you find the value of VTH? VTH is nothing but the voltage source which is the open-ended voltage across the two terminal with the load removed. That is called as VTH. That is here open-ended voltage. Open-ended voltage means here in the circuit, you see, if I remove RL from here, if I remove RL from here, then what will happen is that this load, this point or this two junction will be open circuit, right? Because there is no connection between them, right? So that is an open-ended circuit. So the voltage across those 2 points is what you call as the VTH. That's how we find the value of VTH, right? It is the open voltage between these 2 points after when you remove the load resistor. Okay, and how do you find the series impedance ZTH? How do you find Thevenin's impedance? The series impedance is the impedance of the network between the two terminals with the load removed and the constant voltage source being replaced by short circuit and the constant current source being replaced by open circuit. Which means if you take a network and if you want to find the series impedance, all you need to do is take the network and replace every voltage source with open circuit and replace every current source with short circuit. Then find the impedance between the 2 points. That's all. That's just how we find the series impedance or Thevenin's impedance. Okay. Let me do one problem. Let me just tell you, using a simple circuit. Okay, I will explain to you how to find the Thevenin's theorem. Suppose let me draw a circuit. Okay, let me take up a very simple circuit. I'm going to draw a circuit which is having a voltage source over here, and let that voltage source be called as VS voltage source. Okay, and this is an impedance Z1. This is in here also another impedance is there, that is called as Z2. Okay, and there's another impedance over here that is called as Z3. Okay, and I'll use another pen. This is the load impedance. The load impedance. Okay, I'm going to call it as ZL, load impedance, right? Because it can be any output. I'm going to generalize it. Okay, any output, right? So here, see, when you say impedance, what do you mean by impedance? Impedance means this element can either be a resistor, or it can be a capacitor, or it can be an inductor, or it can be a resistor plus capacitor, or it can be a resistor plus inductor, or it can be a resistor plus capacitor plus inductor. Each of these impedance. Okay, it can be any one of these combinations. It can be a resistor, capacitor, inductor, or any combinations of those three. Okay, that is what you call as the impedance. So that is why I'm explaining to you the Thevenin's theorem of AC circuit. Okay, if it had been a DC circuit, then there's no much difference. Then all these impedances are nothing but pure resistors. That's all. Okay, so here, as you can see over here, this is the impedance. And this is the load impedance. Okay, so your first step to find Thevenin's theorem is to remove the load impedance. Now, what is the meaning of load impedance? Is the impedance across which the output is connected. That is the load impedance. That is what you call as the load impedance, right? It represents the output device. See, for example, in our question, in our problem, suppose if they ask you find the voltage across ZL, or they'll ask you find the current across ZL. In that case, that ZL is the load impedance. Suppose if they ask you find the voltage across Z2 or find the current across Z2. In that case, Z2 is the load impedance. So which is the load impedance? That impedance you have to remove. Here in my example, ZL is the load impedance. So I am going to remove ZL. So what will happen if I remove ZL? This will be the circuit. There. This is the circuit. Once when I remove the load, your circuit will become like this. Z1, Z3, this is 2. See, now the load is removed and the voltage across these 2 points, let me call those 2 points as A and B. Okay, so the voltage across A and B, or the open voltage across A and B, is what you call as the Thevenin's voltage. That is how we find the Thevenin's voltage, by simply finding the voltage drop, or the potential voltage across A and B. If you find that, that is Thevenin's voltage. This is how we find. So let me find that for you right now in this example. Okay, here I'm going to use only these 3 values, okay, and only Vs. So one thing you need to understand, okay, is I'm going to explain to you how to write the equation, and you are going to apply nothing but mesh analysis. Very easy. I'm going to explain to you how to write the equation for VTH purely by common sense. I'm going to explain to you in a very simple manner, and the way how I'm going to do is like this. That is, I'm going to tell you by simply apply mesh analysis. So let this be I1, okay, and let this be I2. Okay, although I don't want you to mark I2 when it comes to the problem, because it's actually a mistake. Marking I2 like this is actually a mistake. But the reason why I'm marking is because I just want you to understand how to write the equations. Okay, but when you're doing the problems, it's always preferable not to draw I2 like this, because the reason is, you all know what the reason is. All of you know what the reason is, because when you remove the load, this end is open. If this end is open, you know that no current will ever flow through an open circuit. If you want current to flow, the circuit has to be complete. Here the circuit is missing. You see, this portion is open. That's why it's called as open-ended voltage or open circuit voltage, because this end is open. So if this end is open, then no current will flow through that. It's a sure. Right? That is the meaning of current. Current means it has to be a closed loop. There has to be some kind of a closed loop if you want some current to flow through it. And if there is no closed loop, no current will flow through it. Or in other case, here in this circuit, in this example, this branch is open, right? This branch is open, and I already told you what is the name of the current through this branch. What is the name of the current through this branch? It is I2. Or in other words, in this branch or in this circuit, the value of I2 is equal to 0. Why it is 0? Because this branch is open. This is what you need to understand. Which branch is open, that current through that branch will be 0. I repeat, which branch is open, then the current through that particular branch will become equal to 0. For example, over here, suppose, like I said before, suppose if Z3 is the load, then you're going to remove Z3, right? So what is the current through this branch? Then this branch will be open. So then what is the current through this branch? I2. Therefore, I2 becomes 0. Suppose if Z2 is the load, okay, just assume, for example, if Z2 is the load, then the current through this branch is equal to 0. What is the name of the current through this branch? It is I1 minus I2. So therefore the current through this branch is 0, or I1 minus I2 is equal to 0. Suppose if Z1 is the load, so then what you are going to do? You are going to remove Z1. So therefore if you remove Z1, then this branch will be open. And what is the current through this branch? I1. So therefore I1 is equal to 0. So that is what I'm telling you. Which branch you're going to open, the corresponding current in that branch will be equal to 0. Just remember that. So what I'm going to do, so here we know that I2 is equal to 0. So now what I'm going to do is that I'm going to simply write the mesh equation like a normal method. I'm just going to write the mesh equation. So here, what is the equation for mesh 1? The equation for mesh 1, let me write that. Equation for mesh 1. Okay, so here the mesh 1 equation is, see here you can see it is I1 into Z1 plus Z2, okay, minus I2 into Z2 is equal to Vs, right? Because this is the positive terminal, this is the negative terminal, okay? This is the positive terminal, this is negative terminal, so this is equal to Vs. This is the equation for mesh 1. Okay, all right. I know that I2 is equal to 0, but I'm not going to substitute that value over here. I'll tell you why, just to make you understand. Okay, so now I'm going to write the equation for mesh 2, or if you want, okay, maybe I'll just put I2 is equal to 0. So since I2 is equal to 0, then this value, this term will be equal to, since I2, let me write that, since I2 is equal to 0, therefore it is what, I1 into Z1 plus Z2 is equal to Vs. Or in other words, what is the equation for I1? I1 is equal to Vs by Z1 plus Z2. Okay, so now I found the value of I1. Okay, fine. Now I'm going to apply mesh 2, or I'm going to apply mesh analysis in this equation. But remember that this mesh is open, right? But just to write the mesh analysis, I'm going to assume that this is a normal current, I2 is flowing. Then only I put the value of I2 is equal to 0. Okay, so like that, let me write the equation. Now this is where it is important, because here in this mesh there is a term called as VTH. What is VTH? Remember, VTH is not a voltage source in this circuit. In this circuit, VTH is an open-ended voltage. It is the voltage across A and B, or it is a voltage drop, or the potential voltage across A and B. It is not voltage source. Remember that. Always remember that. So this is how do I write the equation for mesh 2? Is that here we know what is the over here, right? What is the voltage over here? That is here I1 and I2 is flowing. Let me write the equation. It is minus I1. Since this is mesh 2, I2 is considered as positive and I1 is considered negative, right? So I minus I1 into Z2 plus I2 into Z2 plus Z3. Z2 plus Z3. Okay, plus VTH is equal to 0, plus VTH is equal to 0. So this is the only difference between the mesh analysis and this circuit. See here, you can see that in other circuit there is no VTH and all. Here there is a VTH. What is VTH? VTH is the potential drop. Or in other words, just simply assume, just for fun, just simply assume that there is a resistor over here, and the voltage across that resistor is VTH. That is that same VTH what you have written over here. Okay. Now, why it is plus VTH and not minus VTH, or how do you know whether it is plus VTH or minus VTH? I have already told you before that current always flows from a higher potential to a lower potential. Current always flows from 5 volt to 3 volt, or from 10 volt to 7 volt, or from 20 volt to 10 volt. That is, current always flows from a higher potential to a lower potential. In this circuit, which is the higher potential? A. And which is the lower potential? B. So therefore, if you look at the direction of this current, it is flowing from A to B. See, in this direction, right? Clockwise direction. It is flowing from A to B, or it is flowing from a higher potential to a lower potential. That is why. So that means this is going in regards to your same current, or it is supporting the current. Not, I wouldn't say supporting. It is acting correct exactly the way how the current is flowing. That is what. See here in the circuit is Z3. This is the impedance, right? So you can see this. If you take the I2 is flowing from left to right. So this is the higher potential. This is the lower potential, right? And if you look over here, this I2 is flowing like this and it's going upwards, right? In this branch, it is going upwards. So as far as I2 is concerned, Z2, this is the higher potential and this is the lower potential. So like that is how we mark the potential, not voltage source. This is the voltage source, okay? But this is not a voltage source. This is a voltage potential or drop, just like this. Voltage across Z3 or voltage across Z2, like that. The voltage across A and B is VTH. See, and this is higher potential and lower potential, and this current is flowing exactly in that fashion, from a higher potential to a lower potential. That is why it is plus VTH. This is the equation for VTH. So actually speaking, we don't write equation for mesh 2, we write equation for VTH. That is what you're supposed to write. Okay, just to make you understand that we are applying normal mesh analysis only, I have written like this. But you are supposed to write this is the equation for VTH. Okay, now since I2 is equal to 0, comma, so since I2 is equal to 0, why I2 is equal to 0? Because this branch is open, right? So therefore I2 is equal to 0. So therefore what do we have? We have minus I1 Z2 plus VTH is equal to 0. On other words, VTH is equal to I1 Z2, or, and we know what is I1, we have already written I1. What is I1? Vs by Z1 plus Z2. So therefore Vs into Z2 by Z1 plus Z2. This is VTH. This is an example of VTH, okay? Just to explain to you how to find the value of VTH. This is how we find the value of VTH, okay? Now next I'm going to explain to you how to find ZTH, okay? So how to find the equation for ZTH is, read that sentence and then I'll explain that to you again. The series impedance is the impedance of the network between the two terminals with the load removed and constant voltage source being replaced by short circuit and constant current source being replaced by open circuit, which means in the circuit we take the circuit first. So how to find the value of ZTH is, I take the circuit and I'm going to redraw it, okay? And this time when I'm going to find the value of ZTH, I'm going to replace every voltage source with short circuit and every current source. If there are any current source, I'm going to replace that current source with open circuit. So here in this circuit, your circuit for finding ZTH is this. This is the circuit for finding ZTH. There. This is the circuit for finding ZTH. This is A, this is B, this is Z1, this is Z2, and this is Z3. This is how we find the value of ZTH. That is, ZTH is the impedance between the two terminals. ZTH is the impedance between A and B. So what is the difference between this circuit and this circuit? What is the difference? The difference is over here. That is, I have replaced my voltage source with a short circuit. Short circuit means nothing, just simply short it. That's all. Just simply make the connection or simply join it. That's all. That is the meaning of short circuit. That is the meaning of impedance, or that is the meaning of finding the impedance. That is, if you see any voltage source, you short it, and if you see any current source, if there are any current source circuit, then you open it or make it open. That is how we find the. So that means every element will be exactly the way it is, except there will be no voltage sources and there will be no current sources. If there is any voltage sources, you short it, and if there is any if there is any current sources, you open it, okay, or you remove it. That is how you find it. So like I said, ZTH is the impedance between A and B. What is the meaning of that sentence? ZTH is the impedance between A and B, which means from A to B. Or simply assume like this, that there is a current that is flowing from A, okay, there is a current that is flowing from A and it is going to B. That is the meaning of the sentence. That is, ZTH is the impedance looking through here, assuming that this is the input. That is what it means. Okay, what happens? How do you find it? In that case, how do you find this? What I'm explaining to you right now is a shortcut method of finding ZTH. There is another long method of finding of ZTH, but first let me give you the shortcut itself. So this is the shortcut method. That is, you could assume that there is a current. You have been learning this in school, from school, how to find the value of equivalent resistance and equivalent impedances and all that, right? So here, if you look over here, a current is flowing, and if it's flowing through Z3, right? It is flowing through Z3. So it is Z3 plus, and if it is flowing through Z3, and then after when it reaches this point, it gets divided or it gets splitted, right? It means partial current flows through here and the remaining current flows through here. This current flows in this direction and it goes in this direction and it goes in this direction, whereas this current will flow in this direction, then also it flows into this direction. This is how the current flow takes place, right? So from this current flow, what did you understand from here? That is, these 2 points are the same, right? Because it is a single connection, right? A single connection. Therefore, this point and this point is the same, and this point is also connected to this point, so that is called as B. In other words, this circuit, if you want another way of drawing the circuit, I can draw it for you. That is, it is nothing but it looking like this. There. This is A, the same A, and this is B, that same B. Okay, this is Z3, the same Z3 over here. This is Z1 and this is Z2. See, this is the circuit. See the current direction, exactly how the same, the circuit, both the circuit are the same. You need to understand that, or you need to visualize like that, or learn to visualize like that. These two circuits are exactly the same. So what is the equation? The equation is Z3 plus Z1 parallel Z2. That is the value of ZTH. ZTH is equal to Z3 plus Z1 parallel Z2. Learn to find the value of ZTH using this method, because this method is the shortcut method. I will be explaining you the long-cut method. Okay, so this is the equation for ZTH. Z3 plus Z1 parallel Z2. What is Z1 parallel Z2? What is the meaning of this Z1 parallel Z2? I hope all of you know that. We all know that the total for parallel resistance, right? How do you find the parallel resistance? That is 1 by ZP. 1 by parallel resistance, 1 by Z1 plus 1 by Z2. Or in other words, ZP is equal to Z1 Z2 by Z1 plus Z2. That is the equation. So therefore, this is what is called as Z1 parallel Z2. Okay, Z1 parallel Z2, which means ZTH is equal to Z3 plus Z1 Z2 by Z1 plus Z2. This is the equation of ZTH. This is the equation of Thevenin's impedance. Okay, this is how we find in this example. Okay, so you need to learn to write finding the impedance. Okay, for finding the Thevenin's voltage and finding the impedance, both are very easy. Okay, so that is basically how we find the Thevenin's voltage. This is all you need to find. Now I'm going to explain to you the second theorem, that is the Norton's theorem. And Norton's theorem is exactly the same as Thevenin's theorem, because you have already learned that we can replace a voltage source with a series impedance with a current source with a parallel impedance. So now look at the Norton's theorem. It states that any two-terminal network can be replaced by an equivalent current source and an equivalent parallel impedance. Look at what is Thevenin's theorem. Here it can be replaced by an equivalent voltage source and an equivalent series impedance. But over here it is equivalent current source and an equivalent parallel impedance. Look at the circuit now. Now look at the circuit, the same network, right? The same two-terminal network with a load resistor, and now it is being replaced by nothing but a current source with a parallel impedance. Current source with a parallel impedance. The resistor is the same. See, all I did is I replaced network with these two elements, just like in Thevenin's theorem, how I replaced this network with a voltage impedance with a voltage with a Thevenin's voltage with a series impedance. Like that, over here we have a current source with a parallel impedance. That's the only difference. This IN is what we call as the Norton's current. This is called as the Norton's current. Okay, and Zn is called as the Norton's impedance. It's called as the Norton's impedance. Exactly the same. Okay. Now, how to find the value of the current source? How to find the Norton's current? Just simply look at the statement. The current source is the short-ended current across the terminal with the load removed. What is Thevenin's voltage? How do you find Thevenin's voltage? We find the Thevenin's voltage by it's the open-ended voltage across the terminal with the load removed. But if you want to find the current source or Norton's current, it is nothing but the short-ended current across the two terminal with the load removed. That means what you need to do is, if you want to find the Norton's current in this circuit, if you want to find the Norton's current, remove the load resistor, remove RL and then short it or join these 2 points, and the current between those 2 points is what you call as the Norton's current. That is how we find Norton's current. That is, you remove that load, you remove the corresponding load and you join those 2 points, or you short those 2 points. Just simply make a connection between those, just simply join these 2 points, and then the current through that branch is what you call as the Norton's current. And how do you find the parallel impedance Zn? The method of finding the parallel impedance is exactly the same as how you find the series impedance. There is no difference. Or in other words, you can, with confidence, I can tell you that Zn is nothing but Zth itself. The method of finding Zn is exactly the same of the method of finding Zth. Okay, if the parallel impedance is the impedance of the network between the two terminals with the load removed and constant current voltage being replaced by short circuit and constant current source being replaced by open circuit. Okay, so there is no difference in finding the impedance. There is no difference. This is the same exactly how you found in the Thevenin's theorem. Okay, so let me use the same circuit, okay, to help you understand Norton's theorem. So to understand Norton's theorem, I'm going to draw the same circuit. Okay, so let me draw the same circuit. That is, this is the voltage source over here. We have Z1 over here, then we have Z2 over here, then we have Z3 followed by ZL. Okay, this is Z1, Z2, this is Z3, and this is Vs. Okay, this is ZL. Okay, or your device in question, the load impedance. Okay, so what I'm going to do is, so what is the first, so finding Norton's theorem, the first step is to remove the load. Just like in the Thevenin's case, just like that over here, we remove the load. So what will happen if I remove the load? See what happens, how the circuit will become, remove the load, then the load will be removed, and then you have to join it or you have to short it. So I'm going to short these 2 points like this. See, I removed ZL and then I short it or I joined it. This was supposed to be A and B. Now A and B are the same. A and B are single connection. That is what it means. This is Z1, this is Z2, and this is Z3, and this is Vs. Okay. So now we all know how to find the Norton's current. So this is Norton's current. Basically, this is Norton's current. There, I'm drawing it for you. This is Norton's current. The current through between those 2 points, or after joining them, what is the current to that branch? That current is called as Norton's current. So here in this example, when you want to find the Norton's current, just like Thevenin's theorem, simply apply mesh analysis. So over here, if I apply mesh analysis, how does it look like? This is I1, and of course there is a current called as I2, because this time the mesh is closed. So definitely there's a current, unlike in this case, right? In this case, In this case, the mesh 2 is open, therefore I2 is equal to 0. But here, both the meshes are closed, so therefore there is a value for both I1 and I2. Now, I'm going to ask you how to find what is IN. If you look over here, according to your mesh analysis, according to the mesh analysis that you have used, the name of this current over here is I1, the name of the current over here is I2, which means the name of the current in this branch is also I2, because the same I2 is flowing in this branch. Or in other words, when you want to find the Norton's current, if you want to find the Norton's current, simply find the value of I2. That is what it means. Simply find the value of I2. So now I'm going to apply the equation for mesh 1. So equation for mesh 1. Okay, equation for mesh 1. So what is the equation for mesh 1? Same like before. This is I1 into Z1 plus Z2 minus I2 into Z2, right, is equal to Vs. Now what is the equation? What is the equation for mesh 2? Equation for mesh 2. Equation for mesh 2 is minus I1 into Z2 plus I2 into Z2 plus Z3, okay, is equal to 0. That's it. And what you need to do is you need to find the value of I2, because IN is I2. So what is how do you find I2? We know how to find I2, right? Using Caramel's rule. Or let me before that, let me write it in matrix form so that you won't have any confusion. Z1 plus Z2. This is minus Z2. Here it is minus Z2, and here you have Z2 plus Z3. That is the matrix over here. The matrix over here is I1, I2, and the matrix over here is Vs0. Okay. So now I'm going to ask you how to find the value of I2. Finding the value of I2 is you take the determinant, right? So that means I replace the second column with Vs and 0. So this is Z1 plus Z2 minus Z2. This is Vs. This is 0 by, okay, and the denominator is the coefficient matrix. That is Z1 plus Z2. This is minus Z2. This is minus Z2. This is Z2 plus Z3. Okay, and you find the equation. So what equation do you get over here? This into this is 0, minus or minus becomes plus, so the numerator is Vs Z2 by, and what is the denominator? The denominator is Z1 plus Z2 into Z2 plus Z3, and minus or minus becomes plus, minus Z2 square. There you have it. This is I2, or this is IN. This is the equation for finding the Norton's current, IN. Okay, this is the equation for finding the Norton's current. And the equation for finding Zn, like I said before, is exactly the same. Zn, finding the equation of Zn is exactly the same equation. That is Z3 plus Z1 Z2 by Z1 plus Z2. How do I know that? Is because same method. The method of finding it is exactly the same. That is, we remove that load, and we assume that there is a current flowing from A to B, from one terminal to the other terminal. Okay, and then it passes through this terminal, and then it gets split into two terminals, and then it goes back to B, right? That's how you get the circuit. So that's how we write the equation. Okay, see, now let me tell you one more thing. What will happen if this is the last thing I want to tell you. What will happen if I take the ratio between VTH and IN? What will happen if I find the ratio between VTH and IN? Let me see what will happen. So what is VTH? We have already found VTH, right? What is VTH over here? Where is this? Yeah, it's over here. So what is VTH? VTH is Vs. Let me write that over here. VTH is Vs into Z2 by Z1 plus Z2. This is VTH by, now what is IN? I have already found IN, right? What is IN? IN is Vs into Z2 by, okay, by Z1 plus Z2, Z1 plus Z2 into Z2 plus Z3 minus Z2 square. Okay, this is In, right? This is In. So what will happen now? If I find the ratio, what will happen here? Just simply look at the numerator of these two. Vs and Vs will get cancel each other. This Z2 over here and this Z2 over here will cancel each other. This will go down and this will go up, right? Because denominator for denominator becomes the numerator, right? So therefore this is nothing but this will come on top, right? So you will get is, what you get is, you will get Z1 plus Z2 into Z2 plus Z3 minus Z2 square by the whole thing divided by Z1 plus Z2, right? And this can also, I can write, so if I want, I can separate these two terms. So in that case, what will happen? This will become Z1 plus Z2 into Z2 plus Z3 by Z1 plus Z2 minus this is Z2 square by Z1 plus Z2, right? And these two will cancel each other, right? These two will cancel each other. So what do you get? What you get is, you get Z3 plus Z2 minus Z2 square by Z1 plus Z2, right? And this is equal to Z3 into, see what will happen if I now combine these two terms. So this will become Z2 Z1 Z1 plus Z2 square minus Z2 square whole divided by Z1 plus Z2, right? And Z2 square and minus Z2 square will cancel each other, and therefore you get is Z3 plus Z1 Z2 by Z1 plus Z2. This is VTH by IN. Compare these two equations. What do you get? What do you understand? By comparing these two equations, this equation and this equation, what do you understand? You have understood that ZTH is nothing but the ratio between the Thevenin's voltage and the Norton's current. This is the long cut method that I have told you before. The long method of finding ZTH. That is, another method of finding ZTH is, first you find VTH, then you find Norton's current, and then you take the ratio between VTH and Norton's current. Simply take the ratio between VTH and IN. Then you will get the Thevenin's impedance or Norton's impedance. Same case. Okay. This is what it is. This is what it means. This is another way of finding the Thevenin's impedance. But I will never recommend this method because this method is time consuming. Unless and until if you are very quick about it. You understand? If you know how to write the equations very fast, this method I will never recommend. I will always recommend asking you to find the Thevenin's impedance using this same method. That is, you simply remove the load. And you replace every voltage source with a short circuit, and you replace every current source with an open circuit. Then you find the impedance between the two terminals. This is actually the easier way of finding the impedance. This is the easiest way of finding the Thevenin's impedance or Norton's impedance. Okay. This method you can only use this formula only in one and only one case, and that is if, this is very important, if any element in the circuit, is a dependent source. If any element in the circuit is a dependent source, then use the above equation only. That is what is very important. That is, if there is a single dependent source in that network, if anywhere in the circuit, if there is a single dependent circuit, anywhere in the circuit, if there is a single dependent source, let it be a dependent voltage source, or let it be a dependent current source, let it be a voltage controlled current source, or a current controlled voltage source, or a voltage controlled current source, or a voltage controlled voltage source, whatever, let it be any dependent source. If you see any one dependent source in the circuit, then the only way of finding the Thevenin's impedance or Norton's impedance is using this equation. That is, in that case, you have to find VTH and you have to find IN and you have to find the ratio between those two parameters. If the circuit is having a dependent source anywhere, if you see a single dependent source, because the reason you should understand the reason why. I hope you should be able to understand the reason. The reason is because, like I said, to find the ZTH, I have already told you, to find ZTH or to find ZN, what you need to do is you need to short the voltage source and you need to open the current source. Look at the statement. Look at the two statements. That is, the constant voltage source is being replaced by short circuit and constant current source is replaced by open circuit. Here also same case. Constant voltage source is replaced by short circuit and constant current source being replaced by open circuit, which means you can only apply this technique if that voltage source is constant, that is independent, not dependent. See, not dependent source. You cannot apply a voltage source which is dependent. You cannot apply this formula on a dependent voltage source. So if there is a dependent voltage source, you can neither short it, you can neither open it, you can't do anything of it if you see a dependent source anywhere. That is why to find the dependent source, you cannot apply this shortcut method. Then you have to apply this entire formula. You have to apply, you have to find both VTH and IN and then find the ratio if you want to find this impedance. Okay, so this is basically the theory regarding the Thevenin's and Norton's theorem. Now we can next video we'll be doing the problems based on these two theorems. Okay.